Hello, and welcome to the next installment in the PMI webinar series. I'm Chuck Weber, the Director of Production for PMI. This is a retake of the audio. The slides are the same, but we had some trouble with the first audio. If you saw the first presentation, the audio should be better on this one. Thank you. And back to the introduction. Although most of PMI's webinars have been based on much more current material, we decided to wipe the dust off this older report that we created back in 1999 and present it again for the benefit of those interested. That's not a typo. Back in '99, I was PMI's quality manager, and with the help of an engineering intern that summer, we had a really good time drop testing lots and lots of rope. We did this report and some others. This particular study and other ones like it, prepared by PMI over the years, have been presented at ITERS, which is the International Technical Rescue Symposium, and are always open and shared with anyone interested in furthering our understanding of life safety equipment that we all enjoy using. ITERS Online is a superb resource of virtually all the past research papers presented in the seminars dating back to 1999. It's open to the public, and there's a link to the ITERS Online site available on the PMI webpage. I'll give you those links here at the end of the presentation. If you like some of what you see here today, then you'll love that site. So definitely go check it out. Before getting into our results of the modified testing, or even the UIAA test details, let's touch on the practical limitations of testing textiles quickly. For every test ever invented, there's likely a host of critics, and this certainly applies to the UI drop test. Some say the test is not real world enough. Things like, I use a different knot. That's a rigid test mass. That's not a real belay device, etc. You could debate there's some truth to all that, but at the same time, great care and precision is needed in order to get repeatable results when testing textiles. And the main purpose of lab testing is to ensure that the rope meets minimum safety requirements, the results are consistent between labs, and importantly, useful data is provided to the customer to help make informed buying decisions. For example, look at humidity. 15% or 80% may be absolutely pointless if you're testing a carabiner, but when it comes to textiles and the performance of nylon ropes, it can make an appreciable difference, and it has to be controlled. So things like temperature, humidity, exactly how the knot is tied, preloading the knot, rest time, the rate of loading, all must be considered when testing textiles if you want to have reliable and repeatable results. There's currently open discussion in the UIAA Safety Committee to change the test method in the near future, but for right now, let's talk about the old test because it's still the test. Let's quickly recap the basics of the standard UIAA drop test for a single rope. This is by far the most common use and category. There's also half and twin, but I'd rather not go into those to keep this a little shorter. And it's not what we tested for this study. We're also really just focusing on forces today. I'll make a few notes on elongation, but we're really just talking about the impact force. In a nutshell, the test rope is tied to an 80 kilogram mass. It's 176 pounds. It's pre-weighted to set the knot. And then you carefully position and anchor it as shown in the diagram. Then it's released from the high point for the free fall test. And fall factor in this case is almost the worst case climbing scenario of 2.0. The test configuration is technically a fall factor 1.71, and we'll look into this a little bit more in a moment. During the first drop, both the impact force and the distance traveled, also called the dynamic elongation, are to be measured. Then the rope and test mass are returned to the starting point to rest. There's allowed 5 minutes between drops, and then the second drop is conducted. And all of the drop tests are simply pass or fail, except the first one where the force is measured. Simply said, when the rope breaks, the test is over. Just a few comments here. The 80 kg is considered a reasonable average size climber. In the top of the picture, working our way down, you see the yellow basket is what in the PMI tower free falls down a 30-foot vertical track by way of guide rails. They're just out of the picture on the left and the right. PMI's customized basket design allows us to add additional metal plates to each side and secure them in place so we can do testing like this heavy climber series, and we can also get the basket up to 500 pounds when it's full on each side to evaluate rescue loads on different ropes, devices, and systems. You'll see directly under the tie-in point, there's a 10,000 pound load cell. It's the silver cylindrical device there, and it measures every millisecond. This helps ensure that there's no peak missed in the, because when it hits, it only takes a split second to reach that peak force. It's that top rounded metal piece right behind where the knot is tied in. The big heavy red metal bar you see across the middle, that's just the rigid anchor point. Underneath there you can't see, but there's a smooth, large opening in a metal plate that the rope is threaded through. There's a better shot of that in the video at the end of the presentation. And at the very bottom of the picture there, you see the rope is wrapped 3 times around a bar, and then it's clamped, and the clamp is just out of the picture actually. And this is the standard configuration. Fall factor is a unitless number. It's simply calculated by taking the length of the fall and dividing that by the length of the rope that's available to absorb the fall. So look at these 2 examples. You can see both falls are 5 meters, but they're not the same in terms of shock the falling climber and the system are about to feel. The 2.0 fall factor obviously produces much more force. When you think of the rope as an energy absorber, which is exactly what it is, it makes sense that when you have twice the length of rope, you have twice the capacity to absorb the energy of the fall. Hardware and slings can certainly hold these forces safely, but because they don't stretch, they simply don't absorb any of the energy of the fall. They sustain it, but they don't absorb it. That's the rope's job. One important safety comment here is that a low stretch or static rescue rope should never be used or put to the test in these scenarios as shown, because it may not pass. Even if the rope didn't break, the forces would be much, much higher than allowed by the UIAA drop test, and somebody could get hurt or other gear is going to fail. The simple reason is those ropes don't stretch like dynamic ropes do. They become the weak link of the system. This may be slightly splitting hairs, but the UIAA drop test is not a true fall factor 2.0, as you saw in the example on the last slide. You may find it referred to that way in some sources though. The standardized configuration of the UIAA drop test is as shown. It's technically 4.8 meter drop onto 2.8 meters of rope, hence the 1.71 number. Some sources refer to it as 1.78, but this is kind of splitting hairs, and I'm talking about that. Scratch that. I'm talking that we can discuss further if you're interested at the end. More important than exactly how it's measured is understanding the basic concept that this is a very severe drop test. I just wanted to point out a few things relating to impact force. The upper limit is only measured and required on the first drop of the test. The upper limit for new ropes is 12.0 kilonewtons, or 2,700 pounds force. Part of the reasoning behind this is the force multiplying or pulley effect, as shown on the right of the slide, that happens when a climber falls from above the last point of protection. The force felt in the climber's end of the rope transfers a virtually equal force back through the rope to the belayer's end. It's slightly reduced by friction, but we won't spend much time on that. The basic pulley effect comes into play when you realize the top anchor point, basically pulling upward, has to counteract 2 forces that are pulling downward. So if you're at the upper limit, and if climber feels 12 kilonewtons, and there's 12 kilonewtons on the other side of the rope, that's 24 kilonewtons that the anchor has to hold. And that's basically why slings and carabiners must be rated to 25 kilonewtons. They would fail. On the left of the screen is a commonly used equation that incorporates the modulus of the rope and the fall factor to help predict what the forces will be. I'm not planning to go too far into that, but we can touch on it again near the end, or I'll take questions later. This is the question. As bulleted here, ropes do not really pull to failure in the field. They're simply too stretchy. They can definitely be cut though, and that's the rope's Achilles heel, if you will. Also, if you're only a 100-pound or so climber, you're probably not too personally interested in this subject, as it's virtually impossible for you to generate too much force on your protection system. But if you weigh more than 176-pound test weight, we thought you'd find some of this info useful. Just for the record, here are the UIAA laboratory specs on the ropes used in this test. Important note that each test performed was with a new and unused section of rope from the same production line. I have an interesting thought and some numbers to share with you at the end on what happens after ropes are broken in perfectly normal use in lowers or rappels, and they're then required to catch a hard fall. So the basic plan was to load the new test weights and perform the first drop of the standard UIA drop test. Then we'd load another rope, slightly decrease the length of the fall so that we were testing a lower fall factor. We'd continue like this with a new piece of rope for each test until we measured a force that was roughly equal to the initial force you got with the 80 kilogram test mass. Then we move on to the next higher test weight and keep going. Consider this example. Here's that standard test result again that we're comparing everything to. Here's what we got on one of the heavier test weights in the 1.71 fall factor. Another way to say it is we reduce the length of drop from 4.8 to 3.4 meters, and we get the same impact force. That's also saying the force of 176 pounds and fall factor 1.7 is equal to the force of a 225 pound test weight and fall factor 1.2. I personally like this one because that's close to what I wear toting all my gear. Okay, this isn't exactly rocket science, but it's always a good idea to prove that formulas work in the lab, and in this case they did. We're glad to say that of the 39 drop tests performed for this project, the formulas shown earlier produced results that were always within 10% of the measured value, and 12 of those 39 were even within 2% of the predicted value. Reminder of this simple fact: regardless of the test weight, of course, the higher the fall factor, the higher the force. So here's basically the graphical representation of all 39 drop tests. Every test we performed is a dot on this chart. The y-axis, going up and down, is the impact force measured at the climber's end of the rope. The x-axis in this graph is fall factor. So basically, if you start in the bottom right corner, and imagine there's a dot where 176 pound, there's a dot for the 176 pound test weight, where the 1.71 fall factor and 1866 pounds would intersect, would be in the bottom right corner. It's just not shown on this slide. If you start there, then you'll see the next line up has 4 dots. It's the blue line. That's for 200 pounds. And then the next line above that is the pink one. I'm sorry, you progress up through the weights, you can see the test we did. And then the highest test weight we did was the pink one at 300 pounds. Here's a few more examples of results we felt were getting into dangerous category, and we wanted to point these out. So if you're a 250-pound climber, you might be interested to know this number. Be careful. If you're 275 pounds, you better be a little more careful. If you're 300 pounds, I'd say you're kind of on your own, so be safe. The reality is that very few climbers are this heavy, and again, ropes don't break from being overloaded in the field from high forces. They tend to cut on sharp edges, if they fail at all. Here's the data table from the first 19 drops. Data from this table were graphically shown in the previous slide. I'm not going to spend a lot of time on this, but wanted to include it for those wishing to further review it on their own at a later date. Here's the second half of the data. You can see it's drop number 20 through 39, and I'll leave it up for a minute again. And again, this is just for later review. So after we conducted those 39 tests, at a later date, we wanted to take a closer look at the elongation on certain test scenarios. Not all 39, just the ones you see above. And those results are shown in the slide. Of course, it's simple to say that the higher the weight and force, the more the rope will elongate. But this puts some actual percent elongations with certain weights and fall factors if you're interested. Of course, all these tests were performed on new pieces of dynamic rope. And in real-world scenarios, the ropes will surely have been used for days, months, or even years before ever being subjected to a serious fall, like you're seeing demonstrated in these tests. There's so many varied scenarios on how ropes are used and abused. It's virtually impossible to predict how much strength will be lost or how long the rope will last. Too much depends on how severely it's used. A rope can be destroyed on its first outing, or it can deliver many years of reliable service. As a side note, the research paper mentioned on this slide is a very interesting study that was performed and well documented by a group of engineering students at the Stuttgart testing facility in Germany back around 2002. The full report and many other interesting papers are available on the website of the Alpine Club of Canada, and I'll give you that link at the end of the slide, at the end of the presentation. The take-home message here is shown in that second bullet, that just lowering reduces the rope's ability to absorb energy. No falls whatsoever. They determined that after 80 lowers, the number of UIAA test drops that the rope can hold is typically reduced by half. They use different devices and different scenarios, but that's a pretty good summary of what happened. On a positive closing note though, dynamic ropes undoubtedly have an overall excellent safety record, and that's in large part due to the efforts of both the UIAA to set and promote minimum safety standards and the manufacturers to maintain quality control and continual product improvement. Thank you for your time, and I hope you enjoyed this latest installment in the PMI webinar series. Here are a few good links for test reports and other data. The next slide is a 1.5 minute video that I got from the UIAA Test Site. The UI website shows various items being tested. Right after the video, we'll do the Q&A session, and thank you for tuning in.
if anybody has any questions, feel free to type them in right now, and you should be able to see my screen here shortly. There we go. Okay, Chuck, are you with us still? Okay, we might not have figured out our audio difficulties.
Jess, can you hear me?
Yeah, I can hear you.
Okay.
Okay, and you sound perfectly clear, so that's very good. We don't have any questions yet, and I think that that might have something to do with the quality of the audio that we were getting. We'll give it a couple more minutes here just to see. And I believe, Chuck, correct me if I'm wrong, but I believe you said you were going to go ahead and re-record the audio portion of that for us for the posting online. Chuck, are you still there? Okay.
Yes, I'm here.
We're
Can you
having
hear me?
Okay, I can hear you now. Okay.
Sorry. Yeah, I agree the quality wasn't good on my end when I was listening as well, so I do plan to re-record the audio so that our archive copy will be a better presentation record.
Okay. And that re-recorded audio will be posted with the video on our website, and I will actually go ahead and put that up on our screen right now. So that's the website that the presentation, the video of the presentation will be at, and it'll have better audio so you can actually understand everything that he's saying, and we really apologize for that. And also the slides from this presentation are going to be there, and you'll also be able to email Chuck directly from the website, or his email is also listed on the screen. And we do have one question, and it is, do you plan on trying to do some sort of real-world used rope testing, as you mentioned, such as after 1 or 2 falls and 50 lowers type of situation?
Yes, I'd like to down the road. It's not set yet exactly. We've talked here about bringing in another intern for a session in the near future, and that's a great project for students and people with time on their hands. And but it's great info. I certainly personally enjoy it. It just doesn't pay the bills as much, so we have to try to get some help to make that happen.
Okay, awesome. And there's another one. Okay, has there been any testing of static rope degradation after lowers, so mimicking the dynamic rope testing?
Not that I'm aware of to the same level as that report I mentioned from the group in Germany at the Stuttgart facility. That doesn't mean it hasn't been done. I'm just not aware of one. Generally speaking, I guess I can add that the dynamic ropes, because their stretch is so altered by the heat treatment as part of the production, this is a loose analogy, but it's kind of like ironing clothes. You know, when you apply heat, you've got a nice clean pressed shirt, and then over time it wrinkles again. It starts to lose that shape. Well, the dynamic rope goes through an extra heat process where the yarns are really, they're shrunk further than any static rope would be, and that helps give them more elongation, which is great for climbing, but that does wear off over time from lowers and falls, just normal use really. Of course they're safe, but there is a performance curve like any other synthetic. You know, it loses lubricity over time. It all depends on how much it's used, where it's used, what it comes in contact with. Static ropes, to answer the question, are just so much more durable in that sense. You could do the test, but I think you'd have to do many hundreds and hundreds of lowers to see any appreciable loss. We've tested old ropes that have been hung in caves for a decade or 20 years, and they'll have strength loss for sure, but not even 50%. Like you saw, the report showed that the dynamic ropes were reduced by 50% in their energy absorbing capacity. But it's interesting, it would just take many, many lowers to really damage a rope, a static rope.
Okay, great. And I don't see any other questions. If you do have any, go ahead and type them in right now, and I'm going to start closing this up. If you do have other questions that you don't have time to get in today, or you think of later, you can definitely email Chuck directly. And the PMI webinar series hosts webinars frequently. We do at least once a month, and you can keep an eye on our website for dates and topics. Also, we put all of our webinars and all sorts of other information in our newsletter and on our Twitter and Facebook page, so you can follow us through those venues too and stay up to date with what's going on. And we really appreciate you being here, and we hope that you enjoyed it. And Chuck, thank you so much for doing it. It was very informational.
Good. Thank you, Jessica, and everyone
Have
that attended.
a great day, everybody.
Thanks. Yep.